we're done with single stage gas absorption. That would be the same principle with stripping, only that the transfer in the case of stripping will be from the liquid to the gas, because this time your gas will be your solvent and your liquid would be the phase where you are interested to take a component of. I'm referring to stripping. Now, in the case of gas absorption, just as a review, we're taking a component from a gas phase using a liquid phase. For this afternoon, we will continue with multi-stage gas absorption and stripping as well. Okay. Okay. Please let me know if you can already see the slide on multi-stage material balance for gas absorption. Since I cannot see you, can I have somebody confirm if you could see already the slide?
Yes, miss.
Okay, thank you. So we are now on multi-stage gas absorption and stripping. The notation that you are seeing here is based on John Copley's notation. We're using LO for the feed, and rather for the solvent that is introduced on top of the column. The orientation in this case is horizontal, but you can rotate this clockwise to make it comparable to a column, a gas absorption column, wherein the solvent, the liquid solvent, is LO, and the solvent that carries with it the component of interest taken from the gas phase is the Ln. So it leaves already stage capital letter N, so it's L sub N. And our feed in this case is the gas phase V sub N plus 1. And the lean gas phase, what I mean with lean is it already contains the least amount of the component to be removed from it. So that's your V sub 1. So it is leaving your column at the top. Okay, so this is a multi-stage gas absorption process. The same is true when we have stripping. We only change the transfer, as I've said, but the orientation and everything, the labeling is entirely the same. Okay, now if we'll make our material balance, we need to take the sum of the streams that enters our column. So we have the gas, the feed gas, and we have the solvent here, L sub O. And we need to equate it to the sum of the phases that leaves our column or our system. And that's the V sub 1 or the V sub 1 and the L sub N. So you have it in here. And the sum of these two, it being equated, is also equal to the bulk phase M, the resulting phase wherein the interface, which has the formation of the interface where real mass transfer occurs. Now, if we make a component balance, overall component balance for our system, all we need to do is multiply the phases that we have in here by the corresponding mole fractions in the liquid and in the vapor phases for the L and the V phases respectively. So the labeling follows the labeling, the subscripts that is follow the subscripts of the total material balance. By the way, this is not balance, mass balance, but mole balance, because our concentrations here are in terms of mole fraction. So there's an error there. That should be total mass mole balance. Now, if we have a tray tower design, this one now has the trace 1, 2, until trace capital letter N in here. So this is how we represent it. The original one that was shown to you is horizontal. But as I said, if you rotate this clockwise, you will have your column. Excuse me, and this is your column now. So just the same as the horizontal orientation, only that it was rotated clockwise. So the same thing. This is a tray tower. This could also be a pack tower if we don't have the horizontal lines here designating the trays. Now, for pack towers and tray towers design, aside from the total mole balance or material balance and the total component balance, we can also make a component material balance using the inert streams L prime and V prime. So this L prime here for the solvent is the water part of your solvent. Since most of the time our solvent is pure water, then that would be correspondingly your L prime. And your V prime is that part of your gas which is not the component that you are interested in. So anything other, all the other parts, the remaining parts of the gas phase that doesn't contain your component of interest is the inner part. And just like what was discussed to you as well, when you're using the inner part of the strings here, L prime and V prime, you're going to multiply it with the mole ratios, not mole fractions. So these are mole ratios when we are talking of a two-component system. And oftentimes, and most of the time, it's a two-component system, and we limit all our problems to such systems. Now, this one is also seen in your handbook on equation 14-12. Now, a pack tower design schematic diagram is a lot simpler than the tray tower because there's no need for you to write the trays, like the horizontal lines that you can see here. So you can just have one column, and a corresponding height of the packing material is counted for as one stage. Just like we count one stage in the case of the tray tower as one line in here. Okay, so this is your tray tower schematic, and this is your pack tower schematic. I place it in here because the lower part of your column is numbered 1 and the upper part of your column is numbered 2. Okay? Okay, the slides are not moving. How come I was already talking for 5 minutes, nobody informed me that the slides were not moving? Is it not moving? I did confirm a while ago if you could see the slide in slideshow. Can you see the slide in slideshow?
Ang sa number 40 lang ang slide, miss, ang kitaon.
But is it on slideshow?
No, miss.
Okay. 40. So I've been talking for already 3 minutes, and it's only now that I was notified that you're still on slide 40. Anyways, let me just paste this on. I'll stop sharing for a while. Now, in terms of the pack tower design, if you're going to plot the operating lines, either for gas absorption or stripping, on your equilibrium diagram, so these are equilibrium diagrams for your system, it has X on the horizontal axis and Y on the vertical axis. And this is the corresponding relationship between X and Y for your system. If the process is gas absorption class, then you're going to use the mole fractions of the streams at the bottom of the column, and on the top of the column will be forming a line. And if it is gas absorption, the line will be located on top of the equilibrium curve. So it could be seen here that your operating line for gas absorption is on top of the equilibrium curve. This is especially very important if you're doing the graphical technique in determining the number of stages for your multi-stage gas absorption or stripping process. Now for stripping, if you do the same, but this time you'll notice that your operating line will not be anymore located on top of your equilibrium curve, but rather it's below. Okay? There is no way that these operating lines are going to cross your curve. And if it's gas absorption, it should really be located on top of the equilibrium curve. And if it is stripping, it should be at the bottom of the curve. So this is for your back tower design. Even if it's a tray tower design, the operating lines are still situated where they are supposed to be. So if it's flatted, absorption will always be on top and stripping will be on at the bottom part of the equilibrium curve. Now, if you do away with the graphical approach, I will just explain it later, but in your computation, you will do the analytical process of determining the number of stages of your column. That would lead you also to the height of your column later on. Then you'll be using the Crimser equation. The Crimser equation, which is found in your handbook at in equation 14-33, section 14. Now, in here, in this equation, you will have the A, which is the absorption factor. It is actually, in terms of the graphical interpretation of the formula, it is the ratio of the slope of the operating line, whether it's, in this case, it's gas absorption, divided by the slope of the equilibrium line. So the ratio of the two slopes is the absorption factor. Now, so you have here the formula. So you need the absorption factor A. It is always suggested, class, that you determine this absorption factor, gas absorption factor, for the tower bottom and the top of the tower, and then get the geometric mean of the two A's to get the A that you will substitute in here. It's on the premise, class, that we are not assuming that our operating line is straight. So in the illustration here, you could see that the operating lines are assumed to be straight. But to make our computations always correct, then we determine the A for the top of the tower and A for the bottom of the tower again, and then get its geometric mean. So the geometric mean is actually the square root of the A at the top multiplied to the A at the bottom. So that's the geometric mean, and the value will be 1 that will be placed in here. As for M, that's the slope of the equilibrium line or curve. So if it's curved, as in most cases it is curved, what you're going to do is use the slope of the equilibrium curve at the dilute end. So what do I mean at the dilute end? So let me go back first on our illustration. So we have here an equilibrium curve, and since M there in the formula is a constant, and in the case of the curve it's not a constant, what you're going to do is get the slope of this particular equilibrium curve and the dilute end. The dilute end is this part of your column for gas absorption. So this is the dilute end. You project this part of your operating line on your equilibrium curve and then get the slope of the line that is tangential to the curve. Okay? In the case we're in, you have a curve. You don't have a line for the relationship between x and y. If the problem already gives you the equilibrium equation relating x to y, then the slope of that particular line is the m that you will substitute in Crimser's equation. If not, so you need to plot your operating line. Actually, you only need the location of the point x2, y2, and then project it on your curve, and then get the slope of the tangent line to that particular, to the curve at this particular point. That should then be the m that you will substitute in your Crimser equation. Okay, so that's the m that should be placed in here. This m here. Okay, of course, your YO is the mole fraction of A in the solvent, and this one is the mole fraction of A in the feed, and this is the mole fraction of A on the gas leaving the tower already. This A is the geometric mean of, let's say, A1 and A2. So what you're going to do is get the geometric mean of the two. A1 will be the gas absorption factor at the bottom of the column, and A2 will be the gas absorption factor at the top of the column. So in terms of a formula for this one, then A1 would be computed as L1 over MV1. And A2 is equal to L2 over MV2. Okay, so if you have a curve, so the slope at the dilute end of your curve will be the M that you're going to place there. The slope at the concentrated end of the curve will be the M that you're going to place there as well. So what I mean is this slope should be M1 and specifically M2 if you have a curve. Okay, so L1 and V1 is at the bottom of the column, so this would be the slope at that portion of the column. Same thing with this. Okay, so my orientation here or my representation here for the streams are based on the 1 and 2 numbering. 1 for the bottom of the column, streams at the bottom, and 2 for the streams at the top of the column. Okay, so you get A1 and A2. It's always suggested, class, that you get A1 and A2 and get the geometric mean. Oftentimes, the operating line is not 100% straight. So if it has some degree of curvature, then it would make your answer more accurate if you get the geometric mean of the two. If this A1 and this A2 upon computation are equal in value, then we can conclude that our operating line is really straight. If the gas absorption factor for these two are equal, then we say that our operating line is straight. If not, then we don't have a straight operating line. Now, do you have any question here? So everything you're going to get from the problem. It's very good if it will make things easy if the problem already gives the relationship between x and y, something like that. So y, let's say for example, is 0.5x. So this 0.5 is already the m that goes here, and that's the same m that should be placed in here. There's no need for you to determine the M1 and the M2 separately for your gas absorption if you have already this relationship. This L1 V1 and L2 V2 of course have to be first calculated using overall material balance and overall component balance. You have any questions? Okay, so if there isn't any, so we will continue. So that's for gas absorption, and this is already explained. So if the equilibrium line is curved, M and A will vary. M will be the slope of the equilibrium line on the dilute end. So as illustrated, it's the slope on the dilute end of your equilibrium curve. Or same thing with the slope of the equilibrium line on the dilute end. So A will be then the geometric average. So this is what I've shown to you. This A sub n, this A sub n class is your A sub 1, and your A sub 1 here is your A sub 2. Okay, I suggest that when you use the Krimster equation in determining the number of stages, it would be best, class, to represent the streams by numbering the column top and bottom by just simply 2 and 1 respectively. We need not represent it in terms of n plus 1, 0, or 1. Though if you have encountered this particular page in John Copley's, he represents the solution in two different ways. Okay, in some problems he will represent the solution in this form using his original representation of the streams, that is using subscripts 1, n plus 1, n, and 0. And there are also equations, and there is an equation that is also using the 1 and 2 only, which is much easier to follow. Okay, 1 for the bottom and 2 for the top of the column. And we have this. Okay? Now, for stripping, you have somehow in terms of form, similar in form is the Crimson equation. It's in equation 14, that's 40 in your handbook. But this time, you will be using, instead of y's here, x. And you have here y already. And your A here is still the A that we have in the gas absorption equation. And the reciprocal of this A, this one is, sorry. The reciprocal of this A is what we call the stripping factor S. So whatever is the computed value of A, if you would be asked for the stripping factor, then you just simply have it inverted. Now, you will have a much simpler equation to use, simpler Crimson equation if the gas absorption factor is 1, because it would be as simple as this one. This also has an equivalent in gas absorption. So this is your simplified formula if your gas absorption factor is 1. Okay? Now, so here we are in sample problem number 7. This sample problem number 7 will use the Crimson equation and will have that part wherein the graphical approach in finding the number of stages will also be discussed. Now, it is desired to absorb 90% of the acetone in a gas containing 1 mole percent acetone in air in a countercurrent stage tower. So the total inlet gas flow to the tower is 30 kg/mole per hour, and the total inlet pure water flow to be used to absorb the acetone is 90 kg/mole water per hour. Now, the process is to operate isothermally at 300 Kelvin, and the total pressure is at 101.3 kilopascal. Now, the equilibrium relationship for the acetone A and the gas and your liquid water in your solvent is given by this equation. Y sub A equal to 2.53 X sub A. So this is good because you are already given the M. So determine the number of theoretical stages required for this given separation. Now for this given separation, you are to determine the N. So you are to determine the N. So this is required. Okay, that's the required information. Now, before you start, this is a suggestion and this will make things a lot easier. Your solution will be a lot easier to follow. Before you start solving the number of stages for either gas absorption or stripping, always complete, whenever possible, the values of the phases. So what do I mean by that? Always determine and calculate first the 4 phases, the L1, the V1, the L2, and the V2, because you will be needing all of those in determining the number of stages. You need the overall material balance. You need the overall component balance, whether in the original form or using the inert streams. Either which of the 2 equations you will use, what is important is you find the 4 phases or the 4 streams. So this is our required information. So let me show to you the solution because I already included in the slide the solution. In this case, just place it down here. The process flow diagram is the figure that you are seeing here. So this is our process flow diagram, figure 10.3-3. And the given values are, so for your Y sub AN plus 1, that would be the 1% acetone. Your XAO, this is the mole percent acetone in the solvent, which is pure water, that is 0. And this is the amount of the feed that is to be processed in the column, that's your V sub N plus 1. And this is the amount of pure liquid water that will be used in scrubbing the air acetone mixture. You need to take out acetone from the air. So you have 90 kg/mole per hour. Okay. Now, for you to follow easily the solution here, it would help probably for you to take a screenshot of the problem in here. So, you need to take out 90% of the acetone present in the gas, which is just 1 mole percent of the entire feed mixture of acetone and air. So whatever is this entire amount, you only have 1% of that acetone, and the 90% of the 1% has to be absorbed by your solvent, or it need to be taken out from your mixture of acetone and air. So these are the values. The gas flow rate 30, your water is 90. Okay, since it's pure water, so your X sub AO is 0. And you have this as your very important equilibrium relationship between X and Y. Okay, so I hope you have taken already the picture, so you can go back to that when the solution is presented. So this is our solution. So we need to determine the amount of acetone entering. So that would be 30, your feed gas, multiplied to 0.01 because it's 1 mole percent acetone. So you have 0.30. Okay? Now for the entering air, everything. So that would be 30 minus 0.3, and that would be 29.7. Or you can use this particular formula wherein you still go back to the original amount of the feed, which is 30, and you multiply it to 1 minus 0.01, because your 1 minus 0.01 represents the air in your acetone air mixture. So now you have here 29.7 kilogram mole of air. Okay, this one is for your acetone. If you add the two, that should give you the 30. Now, the acetone living in V1, so V1, where is V1? This is V1. Let me annotate. So this is your V1, this is your LO, this is your V sub N plus 1, and this is your L sub N. Okay, so the acetone that lives in V1 would just be 10% of this 30 that is accounted of, or 0.30 rather. So we have accounted 0.30 kilogram mole of acetone in the acetone air mixture, and that's your feed. So what would live in B1 is just the 10% of this, because the 90% will be living here in LN. As you can see here, 0.10 of 0.30 is 0.03, and 0.9 of 0.3 is equal to 0.27. If you add these two, that should give you the total amount of the acetone that was processed in your absorber, in your gas absorber. So you have 0.30. So this is the acetone in LN, and this is the acetone in V1. Okay, now why do you think this is very important? You need to know the acetone that goes in LN, because you need to add this with water to get the entire value of the LN. And as for the acetone in V1, that would be this 0.03 plus the inner part, which is air. Whatever is the air coming in your column, that would be the same air that leaves your column. So this 29.7 plus the acetone that left unabsorbed, which is 0.03, that would be the V1 that lives here. Now, this is just, but class, an alternative way of doing material balance. You can always do material balance using the equations that were presented in Giancupli's. But the thing is, it does not give you the complete mole fractions or the complete concentrations of all the phases. That is why the amounts here were individually determined. What I mean is, the problem did not give you specifically your YA1 and your YAN plus 1. So you need to determine it like this. That way you can account for the values of the strips. For you to understand better, so you have this already, we can go to the next part. Okay, never mind this one for now. I'll explain it later. So we just have to clear the markings here. But before I do that, do you have any questions? So we accounted for the acetone entering, the air entering, the acetone living in B1, and the acetone living in L sub N. Understand? So I will proceed if there's none. So your V1 will be the inert part, which is the air, I have mentioned already, plus the amount that was left unabsorbed by the solvent. Meaning the solvent was not able to take out this amount because this is the 10% of 0.3. So this is now the total of your V1. So 29.73 air plus acetone, kilogram mole air plus acetone per hour. Now, knowing this is the total V1, you can solve for YA1. So YA1 is the acetone in V1 divided by the total value of stream V1. And that should give you 0.00101. For Ln, we know that water is inert. So this is your water. We add to it the 90% of the 0.0 of the 0.30. The 90% of the 0.30, which is 0.27, this one. Acetone living in Ln would be this plus the amount of water. Of course, water that comes in, it's the same water that comes out. So using material balance. So this is now the total amount of water and acetone living in your solvent phase, in your column. So 90.27. So if you determine XAN, that would be the acetone, which is 0.27, divided by the total, which is 90.27, okay, which will give you 0.003. So you now could see probably the reason why you cannot go straight to the overall material balance equation and the overall component balance equation because you don't have, as I've said a while ago, you don't have the complete set of the concentrations or the mole fractions. The same thing with this V sub 1 and the Ln. It's not stated specifically in the problem. So that's the reason why you need to do it like this. Okay, accounting from what came in, accounting for what was transferred to the solvent, and accounting for what remains. So now we're referring to all of this, we're referring to the A, the acetone in our acetone air mixture. So this is now the values that are very important. They could be seen in the, you will be needing them in your Krimser equation. Now, the first part in here in the solution is just to show to you how the graphical approach was done. And this is this one here that you could see. So I had that part enlarged in here. So what you're going to do, you plot the X and Y pairs, and then in terms of the Y and the 2 representation, so this is for the 2, meaning this is y2, x2, this is for the 1. You have here xa1 and ya1. So these are the pairs of xa1, ya1, and ya2, xa2. Now, this one starts at the bottom of the operating line. This is the equilibrium line. Notice, class, that you have a line because this line is the line that is given to you, which has this particular equilibrium relationship, y equal to 2.53x, okay, if I'm not mistaken. So you have a line. It's not a curve. So in here, you have your operating line. This is your equilibrium line. You have a choice whether you start from the bottom or you start on top. In this case, the number of stages started from the bottom. So you just make stepwise lines in this manner from the operating line to the curve, like this. So this is the 4th, this is the 5th stage, and there's still another one in here. So if it's to continue, it would have been like that. So you still have another big triangle here. But you're only until here, so you approximate this part here in terms of percentage, if we will continue drawing here, I'll just draw this one. If you continue drawing, how much is this area of the entire area of that particular triangle? And that would be the percentage or the decimal value that you're going to add to 5. Because for 5, it's only until here. It did not still reach this point wherein you have y1 and x1. Okay, so you have to approximate this part here. So your answer is 5 point something in terms of the total number of stages using the graphical approach. You can do this, but of course, what you will be utilizing in the board exam will be the analytical approach. Okay, so I'll clear my markings here. So you just draw your operating line using the coordinates, as coordinates the mole fractions, then do this stepwise line. That's graphical. Using Krimsker's equation, so that would be on the next slide. So you have already the V1, you have the YA1, you have the LO. Now the XAO is 0 because your solvent is pure water. So it does not have acetone. And you have this as the equilibrium relationship. So it says here that M is equal to 2.53. So it as suggested, you are to determine both A1 and A2. So in this case, this is LO and B1. So this is actually equivalent to A2 and the 1 and 2 representation. This is A1. Okay? Now you determine, so this would be now L1 over MV1, and this is L2 over MV2. I'm using here the alternative formula if the tower is numbered 1 here and you have 2 here. You have here the gas and you have here the liquid. Okay? So it was emphasized last meeting that you have the gas introduced at the bottom and you have the liquid introduced at the top part of the column. Okay? So this is on that orientation. So with all 4 phases known already, all L's, all V's known, then you can determine the 2 absorption factor. One for the top of the column, this is the concentrated N, and the other one at the bottom of the column, which is the dilute N. Oh, sorry, this is the concentrated N, by the way, and this is the dilute N. So after you have substituted the values, so you just substitute 90, the slope is 2.53, your V1 is 29.73 as computed in the previous slide. You'll be getting this for the A1, 1.20. For your A sub N, you need the L sub N, that's 90.27. The M is still 2.53, and your V sub N plus 1 is the amount of the feed gas that entered the column, which is 30. You could see that there's a slight difference in the absorption factors. So meaning your operating line is not really 100% straight. So it has some degree of curvature. Okay? You take the geometric mean. So this is the geometric mean of the 2 absorption factors. Now, since you already have the A, all you need to do is substitute everything on the Krimsker equation. So you need, in the case of gas absorption, you need the Y's here. And you have here the M, and this is X sub O. X sub O is 0 because we have pure water in our solvent. And you have 1 minus 1 over A. So this is your geometric mean of the A. So your number of stages is 5.04. Analytically, your number of stages is 5.04, which compares closely with what we have in here. So in here, it's around 5.20 as stated. As stated in here. So which of the 2 is more accurate? Of course, the analytical process of determining the theoretical number of stages is more accurate than the graphical. Now, Before I go to the next part of the lesson, do you have any question here? Determining the number of stages. So that's the graphical process. You just need to plot. Does not need a lot of computation, but of course it's crude. The value that you'll be getting is crude. And by the way, when you do your writing of the steps, it has to be straight, which reminds me of the solutions that you have submitted me in the distillation problem. Your operating lines should be properly constructed, and your steps have to be straight. Some of you even draw like this. It has to be straight. Your horizontal lines have to be straight, and your vertical lines have to be straight. In itself, it's already a crude estimate. How much more crude it will be if you don't do the steps properly. Okay, so if there aren't any questions here, then let me proceed to the next part of the slide. So now it goes to that part wherein you need to determine the minimum solvent requirement to effect a given degree of separation. What is the minimum solvent requirement if I intend to, for example, recover 90% of my solute from the gas or from the liquid? So that would be answered by this particular part of the discussion. Now, graphically, when we determine the minimum solvent requirement, what we do with our operating lines is this. So this is your operating line for gas absorption. This is its original orientation. What we do, we move this point here and make it rest on the equilibrium curve or on the line. So we move it horizontally until it reaches your equilibrium line or curve. And then you draw a line connecting the original point determined by x2 and y2 and make it tangential to the point that you have projected here. So this is now your x1 maximum. This is the corresponding mole fraction resulting from the maximum amount of solute that is transferred in your solvent liquid in the case of gas absorption. So we use this, we use the same formula y equal to mx to determine this particular x sub 1 maximum. Okay, so for a particular value of y1, which is given in the problem, or either you determined using material balance, you will determine the x1 maximum using the equilibrium equation. If, for example, I will use the equilibrium relationship of our previous sample problem, and let's say this y1 as given in the problem is 0.03, example ha. So your y1, your x1 maximum will be computed from that. This is your x1 maximum. This x1 maximum is the x1 that you should substitute in your component material balance using the inert streams. That way you can find the minimum solvent requirement in the case of gas absorption. If it's gas absorption. If it is stripping, it would be this graph that we're going to use to illustrate the concept of stripping. So in stripping, you have this operating line, and this could be your equilibrium line or your equilibrium curve. This is your original operating line for stripping. What you do, instead of moving this part here, the top, we move the top part in here horizontally. This one, we don't move it horizontally, but rather we move the point vertically. Okay, this one. So in this case, you'll now be determining the y2 maximum. So how is that? So from the same equation, y2 maximum is equal to 2.53, and you should be using here the x2. the x2 that you have determined or either given in the problem. So what is the maximum amount recovered by your solvent gas in your stripping process using this equilibrium relationship? So the Y2 maximum that you have determined from this equilibrium equation will be the Y2 that you will use in the overall component balance equation. That way you can determine the V2, rather not necessarily V2, but V prime minimum, the minimum solvent requirement. Now, I say V prime class because your solvent in stripping is already the gas. So it should be V prime minimum. I am emphasizing the prime because oftentimes, class, in this type of problems, you're using the overall component balance equation using the inert streams. You're not using the L1, X1, or V1, Y1, and all those sorts of things, but you're using just the L prime and the V primes multiplied to the mole ratios. Now, it would be clearer if I will show to you the equation that I mean. Before that, so in absorption, recovery is maximum. So you see there, it's X sub 1 maximum when inert solvent flow rate is minimum. And that inert solvent flow rate minimum is represented by L prime minimum, because it's actually this one that we initially determined. And then based on the amount of solid present on it, we determine the entire L, and that's actually the LO, equivalent to L2 in gas absorption. In stripping, recovery Y2 is maximum, or Y2 max, when inert solvent flow rate is this, V prime minimum. That's in the case of stripping. So we maximize X1 in gas absorption. We maximize Y2 in stripping. And we use the total component balance equations using the L primes and the V primes. Now, as to liquid gas ratios, the actual liquid gas ratio, or that is the solvent circulation rate, normally will be greater than the minimum by as much as 25 to 100%. The actual amount used for the solvent is most of the time, class, either 25% more than the minimum, or it's even twice the minimum, because it could be even up to 100%, meaning you double it. You double the minimum amount, and that's the actual amount of solvent that you are going to use in the process. You compute the minimum solvent requirement, and in the process, what you're going to use is 25% of that computed minimum or more, so even up to 100%. But in the case of optimization, that is, of course, you need to consider the cost of using a lot of solvent, because of course your solvents have cost, especially if it's not pure water. Even if it's just water, it would still cost you. So for optimization of the liquid to gas ratio in terms of total annual cost, it often suggests that the molar liquid to gas ratio should be about 1.2 to 1.5 times the theoretical minimum. And this is for gas absorption. We actually follow this for stripping because they are on the same range. So 20 to 50% higher than the minimum as well for stripping. Now, since we have here a range of value, the actual amount that will be used in to optimize the process, we use the larger value in the range. So we use the 50% more. So determine first the minimum. Determine the minimum solvent requirement. In the case of gas absorption, that would be L minimum. In the case of stripping, that would be V minimum. And then what you do, you multiply it to 1.5 if you want the optimum. So B optimum will be 1.5 of the minimum. Here, L optimum will be 1.5 of the minimum. So determine first the minimum, then just add 50% to that. that would be your optimized solvent requirement, or the optimized solvent to be used for your process. Here's a sample problem on the determination of, take note, the optimum number of trays. Since it's asking for not the theoretical number of trays, but the optimum number of trays, then this must be based on the optimum solvent requirement, which is based on the minimum solvent requirement. So if we're going to have our solution plotted in terms of steps, we first determine the minimum solvent, then determine the optimum solvent, and based on that optimum solvent, determine the optimum number of trays. Because the solvents that were used, whether the solvent that you are using is appearing in the formula for the Gauss absorption factor or in the stripping factor. So there's a need for you to determine the appropriate amount of the optimum solvent to use. Okay? Now, we'll read this problem after our break. We'll have a 5-minute break. Then after 5 minutes, we will continue with this sample problem. So in this case of the sample problem number 8, you are given a tray tower which is absorbing ethyl alcohol from an inert gas stream using pure water. So your solvent does not contain ethyl alcohol. Now the process is at 303 Kelvin and 101.3 kilopascal. The inlet gas stream flow rate is 115 kilogram mole per hour, and it contains 3.3 mole% alcohol. So of this 115 kilogram mole per hour, 3.3% of that is alcohol, and it needs to be removed using water, in this case pure water. The equilibrium relationship is given by the equation y equal to 0.78x for the dilute stream. Determine the optimum number of trays, and in this case the optimum number of trays is actually 4. So how this value was computed, so let's go to the next part of the solution. So if we're going to draw our gas absorption tower, so this is using the nomenclature 1 and 2 for the bottom of the tower and for the top of the tower respectively. So we'll just be using L1 and B1 here at the bottom, and we'll have L2, B2 here on top. Now in my representation, I use the original representation of John Publius for the streams. But I placed here 1 and 2 just for you to know that this is 1 and this is 2. Now your recovery, let me go back to the problem, is 90%. So place there 90%, and this is our equilibrium relationship, equilibrium equation, y equal to 0.78x. Now this is the amount of the feed gas which contains ethyl alcohol, and this is the mole fraction of ethyl alcohol with air in our inert gas, in our gas mixture. Our solvent is pure, so you have XAO equal to 0. Y sub AN plus 1 is 0.033 because we have 3.3% ethyl alcohol in our air ethyl alcohol mixture in our feed. Now, if you do material balance overall, that is, so you have LO plus B sub N plus 1 equal to LN plus V1 equal to M. We can also write here LO as L2 and this B sub N plus 1 as B1. So L2 plus V1 is equal to L1 plus V2 equal to M. So that is using the numbering here that I indicated. Now our component balance, overall component balance, is patterned after our overall material balance, and we just simply multiplied the streams by the mole fractions of A in this stream. So you have this one. An alternative equation that comes in handy, especially if you want the minimum solvent requirement, is the overall component balance using inert streams. So you have L prime and V primes now multiplied to mole ratios, not mole fraction. So this is actually XAO over XBO. Okay, in the case of XAO is if we have ethyl alcohol but we don't have in our solvent, and XBO, which is 1 minus XAO, is actually your water. The same principle should be applied to the other mole ratios here. Because in all of our streams, we only have a maximum of 2 components present. Okay? Now that's it. Now the next thing that we do is we substitute the values. So for our first equation, we have LO plus 115. This is for our feed, and L1 plus V1. So if you notice in our first equation, you have 3 unknowns. Now if we set up our second equation using the original phases, not the inert amount, so you have 2.20. This is your solvent, and it doesn't contain ethyl alcohol, so it's 0. And this is your feed containing 3.3% ethyl alcohol. More so, it even makes things complicated because this first term will be 0, and you have now 4 unknowns in the second equation. So since our 2 equations have 5 unknowns already, you have LO, you have L1 and V1 for the first, so 3 plus the XA1 and the YA1. We will consider another equation. So we will determine the primes first, because we will try to utilize the overall component balance using the inert streams. So L prime in this case is just LO because XAO is equal to 0. Doesn't contain any ethyl alcohol. I'm referring to the solvent. Your V prime is your V sub n plus 1, which is 115, times the quantity 1 minus 0.033. Now, we are actually accounting for in here the presence of air only in our feed. And air is just 111.21. So, I have placed in there that the L prime and the V primes are the inner parts of our streams. Now, the ethyl alcohol unrecovered, the thing that remains in V1 is actually 10% of what entered. So, what entered is this. This is the amount present in the feed, and what remains is just 10%. So it's the unrecovered ethyl alcohol, and this is the value of that. Now your V1 will then consist of this unrecovered ethyl alcohol plus this V prime, which is the air. The air that enters your column is the same air that leaves the column because it's inert. Its value is unaltered. So what happens is you add 111.21 to 0.3795. That should give you this V1. Okay? V prime plus ethyl alcohol unrecovered is 111.5895. Then we can get also Y1 based on this unrecovered amount, which is 0.3795 divided by the total V1. And this is your Y1. So in the original equation, so far, you have your Y1 and you have your V1. That's it. And you still have the L1 and the XA1 unknown. The LO still is also unknown. So you still have 3 undetermined amounts. So we will proceed, if you don't have any questions here in this part, to the next slide. No question here. Okay. So we'll proceed to the next. So since the optimum number of trays is based on the minimum solvent requirement, so I have mentioned that before we started solving this one, we solve first for the minimum solvent requirement, and that's the L prime minimum based on Xn maximum. So determining the L prime minimum based on Xn maximum. This Xn maximum class is actually equivalent to, based on the slide that was shown to you a while ago, X1 maximum. Based on the representation 1 for the bottom of the column and 2 for the top. So this Xn is actually at the bottom using the original representation of Giancuclis. Okay? Now, next is, we have this. So, your YAN plus 1 is equal to 0.78 X sub n maximum. Or shall we say that this is now taken from, actually this was taken from your Y equal to 0.78X, the equilibrium relationship between X and Y. So what we did, in order for us to determine the X1 maximum, we need to know the M. In this case, that's 0.78. This one, this YA sub n plus 1 is actually your Y1 in our orientation. If you recall the operating line, that we need to move the Y1 horizontally and get the X1 maximum. So this Y sub AN plus 1 is actually your Y1, because this Y sub AN plus 1 is the mole fraction of the feed gas at the bottom. And the bottom representation will all have subscripts of 1. So that is why we have here Y1. So from this original equation, using the equilibrium relationship, now we have here a formula that will help us determine the X1 maximum, also represented as X sub n maximum. So we substitute the 0.033 here. This is the mole fraction in the feed of ethyl alcohol. So you have that also as your Y sub AN plus 1. 0.033, we divide it by 0.78, and this is now your X1 maximum or X sub n maximum. If you recall, I said that this is the one that you will use in your component balance. That way, you can determine first the minimum solvent requirement, which is the L prime. So what's being done in here is this. So you have your L prime. So this is actually your L prime. And let me just erase this one. It's not L1. Okay, so this is your L prime, and this is your X AO over 1 minus XAO plus V prime. So the thing that, and this is your solvent, and the thing that entered is your Y AN plus 1 over 1 minus Y AN plus 1. Okay, equal to another L prime. So you have now it labeled as minimum, and this one would be your XAN over 1 minus XAN. You have here V prime, you have here Y1 or YA1, 1 minus YA1. So we substituted values here. The only unknown is the L prime minimum. It's 0 here because we have a pure solvent. This is the mole fraction of A, ethyl alcohol in our feed gas. This is the X1 maximum, the XAN max, we computed from the equilibrium equation. And this one is the computed YA1 that was shown to you in the previous slide. Okay, I will clear my markings first so you would see. So this is your YA1, and it's in here. We computed it in here on the previous slide. This one, 0.0034, based on the percentage recovery. Okay, so you have the now. Now, you have already the L prime minimum. So based on principle that optimum, if you need to optimize the process, we use 50% more than the computed minimum solvent requirement. So you multiply it by 1.5, and this is now your 115.92. So this is the optimum solvent requirement. Now use this value for L prime minimum and solve for X sub n using equation 3. Equation 3, which is your overall component balance equation with the inert strips. So you have this now, the L prime optimum, which is 115.92. You will replace the L primes here by that amount. Okay? Now you have the V primes the same. Your purpose in here is to determine the new X sub n. This is the new X sub n that you will use in determining the number of stages. Why will your X sub n be changing? You may wonder, na-determine na na-miss ang optimum solvent requirement. Why would we still determine a new X sub an or a new X sub a1? Why should we determine it? No, of course, common sense will tell you your X will be different because you're using more solvent this time. You're using more solvent than the minimum requirement. So this one, the original, will be changing. So this one now will be changing, and the value is 0.0286. The one that you have accounted for in here uses the minimum solvent, while this one is using the optimum amount. So malain din siya. This 0.0286. Now, determining the new X sub an or X sub a1 in this case will of course require that you will have a new L sub n. Malain ang imo nga L sub n because in the first place you're using 50% of your solvent requirement. That's the thing that you introduce into your column. You introduce 50% more for your solvent in your column. Naturally, the solvent that will leave the column will also be changing. So that's the reason why you're computing for the new L sub n. You computed the X sub n based on L prime optimum, and then you compute as well for the new L sub n using the computed X sub n. Now, this particular formula came from this one. So your L sub prime optimum, this one is actually equal to L sub n times 1 minus X sub n. Okay, L prime optimum. L prime optimum is equal to L sub n times 1 minus X sub n. Using this X sub n that you have computed, you will determine again the L sub n. So the L prime optimum value of 115 was divided by 1 minus 0.0286, the new amount for X sub n. And its value now is 119.33. 119.33 for L sub n, and this one, the 1.5, this is your L sub O, equivalent to L sub 2. Why compute for the new L sub n? Because you have a new L sub 2. You will need this in determining the gas absorption factor A. So as such, it is needed that you determine it. Now, where's this one? Do you have any questions before I go to the next slide? So the process is actually procedural. It's really procedural. Nothing so critical. Nothing that will require critical thinking here. Just do it step by step. Determine L prime. Determine L prime minimum. Determine X sub n. Determine L sub n. Okay? Then determine, of course, the rest of the gas absorption factors using the Krimser equation, determine the optimum number of stages. Okay, I will clear my markings here if there aren't any questions. Then we will proceed to the next slide. So to summarize, sorry class. So this is your feed. This is the amount that left your column using 90% recovery. So what is left is just 10% of the ethyl alcohol here. We have computed this one originally. Nothing changed with this two. Wala sak may nag-change ini na duha. Ang nag-change ining duha. This is your L optimum. Let me go back. That's your L optimum, the 115.92. And the resulting L sub n because of this L optimum. This was computed using the component balance equation using the L primes and the V primes. Okay, we determine the Ln using that. Okay, then we determine the gas absorption factors for the concentrated end and the dilute end of your column. So this one is for the concentrated end, this is for the dilute end. So you just substitute. The M is fixed for the 2 because you're given that already. This is your geometric mean. If you're just going to look into the gas absorption factor values up to 2 decimal places, you will conclude that it's a straight line. There's a little curvature because if you add more digits to that, they're not really that equal. So dutay lang ang curvature for your operating line in this case. So we use this gas absorption factor in our formula together with the X, Y. This is for the Y's because this is gas absorption. XAO is still 0. So this is the optimum number of stages for this particular operation. So since it's optimum, it was based on we start with the minimum solvent requirement. We go to the optimum solvent requirement. We determine the corresponding change in the X sub AN or the X sub A1 because there has been a change in the solvent used. And we also determine the corresponding L sub N because of this change in the L sub O. Then after we have completed all our streams, just like the way you see in here, just like the normal problem determining the theoretical number of stages, you are required to determine the gas absorption factors for the 2 ends of your column and substitute everything in Krimser's equation. Do you have any question here? Okay. If there aren't any questions, then we will proceed. Now we go to the design of our column. So far we just determined how many stages should be there and what would be the solvent requirements. Should it be optimized or should we want to know the minimum solvent requirement? Now this time we're going into the design of the column, and if we talk about the design, it considers whether we'll be using packing materials or we'll be using only trays. And if it's packing material, will it be the structured packing materials or the random packing materials? So we first have the pack tower. So this is our pack tower. Our simple schematic for a gas absorption column is that the liquid is introduced on top. So you could see here the liquid inlet, and the lean gas, the gas in which you have already recovered the component that needs to be taken from it, is leaving the top of the column. This is where your feed gas is introduced, and this is where the liquid leaves the column. So this is the packed section. So in terms of packing materials, we have what we call random packing materials. So these are examples of random packing materials. In your handbook, you even have a more comprehensive list of these random packing materials. Then actually we only use two types, and we also have the structured packing materials. Now, I have here a video. Let me know if you could see it for random packing.
Random packing has been around since the earliest days of commercial columns. Initially, extremely non-uniform packing, such as crushed rock and jack chain, were used. First generation packing was more uniform and consisted of cylinders such as the Raschig ring. Second generation developments in the 1960s moved to enhance the amount of surface area per volume of packing by including slots, holes, and fingers. Typical second generation packing are saddles and the Paul ring. Third generation proprietary random packing has been on the market for several years. They all have high open area with complex surfaces in an attempt to maximize vapor-liquid contact and minimize pressure drop. Examples include the Sulzer Kimtech Nutter ring, the Koch Glitch Cascade mini rings, and the Norton IMTP. If we visualize how these random elements would come to rest in a packed bed, we can differentiate between the through flow and the around flow types. The distinction turns out to be quite significant and is related to the ratio of form drag to skin friction incurred by flow of vapor and liquid through the packing. All modern random packing is of the flow-through type with reduced form drag.
So that's for the random packing materials. This time we have the structured packing materials.
Most of the commercially available structured packing is made from corrugated sheets. Crimped, corrugated sheets of metal are positioned so as to create flow channels for the vapor and promote liquid distribution. The combination of efficient use of surface for mass transfer plus the near absence of pressure loss to form drag results in the favorable pressure drop to theoretical stage ratio. The larger the crimp size, the larger the capacity, but at the cost of lower efficiency because of decreased surface area. Wire gauze packing with its low pressure drop is mostly used in distillations with low liquid rates. Other less common and older types involve meshes and grids of varying degrees of fineness. The orientation of the grids is alternated to enhance mass transfer. The efficiency is low, again due to the low surface area, but the fouling resistance is high.
Okay, so those are the structured packing materials. So both your random packing and structured packing materials have one goal, and that is to improve the contact between the two phases, the liquid and the gas. So you want as much as possible to increase the interfacial surface. That way, there will be greater mass transfer that will occur. So whether it be coming from the gas phase or from the liquid phase. Now for your tray tower, so this is how a tray tower looks like in a simple illustration. So you have the gas flowing upwards and the liquid is guided through this downspouts. We call this downspouts or downcomers. So this guides the liquid. It flows horizontally here, and then flows in here horizontally downwards as well. Okay, so in the process, your liquid and your gas flows counter current as well to each other. Though you have here a tray, so you don't have anymore the presence of your packing materials. Now, your tray tower can have different openings for vapor to pass through. So it could be perforated, it could be in the form of valve caps or bubble caps. So valve caps are illustrated like this. Bubble cap, so it's more or less like a valve cap, but in this case, you have here a more elongated cap covering the opening for the bubble cap. Now, this is a tray, as an example of a tray with valve caps. So your tray tower can have any of these openings. Now, in terms of the design of our column, we design it in terms of its diameter, how big should it be, and in terms of its height, how tall should it be. Okay. Now, in terms of diameter, what do we use, or what principle are we using? That way we can come up with the size of our column. So actually, class, when you speak of the size of the column, it refers to the diameter, not the how tall your column is. So as to the answer to my question, what do you use in determining the size of your column or the diameter of your column? We use the pressure drop, or we use the condition what we call as flooding. That way we can design a column that will not be flooded. So we determine the pressure drop. That way we can correctly as well determine the flooding velocity. After we have determined the flooding velocity, we can determine the tower diameter. Now, this procedure is for the pack tower because we have a different formula for the tray tower. So how do we determine the pressure drop for a pack tower? And that is given by the formula that you see here below. So the pressure drop due to flooding is equal to 0.115 times the packing factor raised to 0.7. This packing factor, class, is taken from a table. Your handbook has a comprehensive table on these packing factors based on the packing material that is being used. So the way it's presented in your handbook is that you have one cluster for random packing material and you have another cluster for structured packing material. Now, each of these clusters have their set of characteristics, and one of those is the packing factor. You just need to look for the F sub P, and that's the packing factor. Knowing the packing factor will tell you what would be the corresponding pressure drop in your tower at the condition when it is said to be flooding. Now, what is this flooding condition? So this is a condition, class, in your tower wherein your solvent that needs to excuse me, that needs to leave your column at the bottom, the solvent that carries with it the solute, or the, let's say, the contaminant in your gas mixture. Remember, your solvent is introduced on top, so it flows down, and it should be discharged at the bottom of the column. Now, during flooding, class, this does not occur. Instead of it going down at the bottom of the column, it goes up together with the gas. So both the liquid and the gas lives at the top of the column. And that's a condition we call flooding. We don't want that to happen because number one is you don't achieve your main objective, wherein there should be separation of the, let's say, that component in your gas from the rest of the components that it is with in the feed gas. So if everything lives at the top of the column, then you are not able to recover what you need to recover. So that's flooding. Now, how do we use the flooding velocity to design our column in terms of how big it is, in terms of its diameter? So the usual designs is using actually a range of 60 to 80% of the flooding velocity in computing for its tower diameter. Now, since this is the range, class, now since we want to limit the possibility of flooding in our column, we use the the least value in the range, and that's 60%. What we do first, using the flooding correlation diagram, which I'll be showing to you in a little while, we determine from that particular diagram the flooding velocity. We determine the flooding velocity. Since we know that at that particular linear velocity, our column will be flooded, so our linear velocity will have a corresponding mass velocity for our phases, the liquid and the gas. Since we know already that at that particular velocity it will be flooded, we would like to reduce that particular velocity. By how much are we going to reduce it? We're going to reduce it by this much. 60%, not 80% because that's very conservative. So we use the 60%, a lot lower than the condition at flooding. So determine the velocity when it is flooded and multiply that particular flooding velocity by 60%. That way you can design your column properly. Now in determining the flooding velocity, because you need that in your flooding correlation diagram, you need to determine this delta P at flooding. So a very simple thing which needs only for you to take from a particular table for packing materials the packing factor. Once you have this, then you are ready to use the flooding correlation diagram. Now our flooding correlation diagram has two sets. So we have a different flooding correlation diagram for random packing, and we have a different flooding correlation diagram for structured packing. So you use the appropriate flooding correlation diagram to design your column properly. Okay, so this is actually the steps in determining the column diameter, of course, which needs also for you to determine the pressure drop. So as I have mentioned, you need to obtain the packing factor from a table. Let me check if it's already in here. So this is the table that I am referring to. I just took this from Jan Kuplis because this is just a short list from Jan Kuplis. In your handbook, you have a very comprehensive list of this one. So you have on the top portion the random packing materials, and in here you have the structured packing materials. And in the second to the last column, you have the packing factor. So you have two sets of columns here, one that is in English and the other one that is in SI unit. So per foot, and this is per meter. So you will use the value depending on the values that are to be worked out in your problem. So if the problem gives you English sets of units, you use this value. If it gives you SI sets of units, you use the second one. The same thing is true with your with the tables that you have in your handbook. So for example, you are given a pack tower using rushing rings with the nominal size of 1 inch. So you just read in here its corresponding packing factor. So it's 179 per foot, equivalent to 587 per meter. This is where you're going to get your packing factor. Now, if it's a structured packing material, the commonly used structured packing material is either the Norton Interlocks or the FlexiPacks. So let's say we'll have the Norton Interlocks 2T. So you also correspondingly read here your packing factor. Whichever of the two values here is appropriate to use. Okay, this is the table where you take the packing factor, which you need in step 2. You need to determine the change in the pressure drop specifically when your column is flooded. Now, please take note of the set units for the flooding, or rather for the pressure drop. It's in inch water per foot of packing material. The unit of pressure here is in inches water per foot of packing material, and this is our formula. So from the value that you have in one just to substitute here on this particular formula. The third thing that you need to do is find the corresponding flooding gas velocity. So this is what I mentioned. You determine the velocity in which your column will be flooded. So that's find the corresponding flooding gas velocity using the pressure drop correlation in the figure, meaning you're going to use the computed delta P that you have in here. Typically, class, your flooding velocity, the linear velocity would be 6.6 feet per second or 2 meters per second. Linear velocities, that is, your column will be flooded already. At this, how much more if it's even higher? So your column will be flooded already. Now, speaking of this correlation figure, what is this correlation figure? I'll just show to you what it is. We'll solve a sample problem next meeting. This is your pressure drop correlation, and this is where you're going to get the linear velocity when your column is flooded already. You see this small v sub g? That's the linear velocity of the gas when the column is flooded already. Okay? Now, all of this, of course, you need to acquire first. You need to determine the densities here. You need to have this. Normally, this is given in the problem, the ratio of the liquid and gas flow rates. Once you have already this x value, the curves that you have here, class, are the delta p's. The delta p's that you have computed based on step 2 here, the delta p. So you're going to locate that delta p in here. If it's not among specifically the curves in here, then you can approximate. So using your x value, your flow parameter, you go up, rest on a particular curve based on the delta P computed, and then read here your value for the capacity parameter. It does not still give you yet the linear velocity, so you need to substitute all of this. You need the kinematic viscosity. You need to determine that. You already have your packing factor, and together with the densities here, you also have the densities here to get the linear velocity. Once you have the linear velocity, class, using the volumetric flow rate of your streams, you'll be able to get the cross-section of your column. Getting the cross-section of your column will lead you to the diameter of your column. That's how we determine the diameter or the size of our column. So choose diameter such that gas velocity is about half of this. In our case, we're going to use the 60%. This is even more safe. This is safer. Half lang din siya, 50% of the computed flooding velocity at flooded condition. But we'll use John Copley's illustrations wherein he's using 60% of the velocity at flooding. Okay, so the typical design for your column, that way it will not be flooded. Linear velocity is 1 meter per second. But in our case, it depends on the size of your column. So you increase the diameter, of course, you decrease the velocity if you increase the diameter. If you decrease the diameter, you also increase the velocity. Okay? And then after that, find the pressure drop in the column from the pressure drop correlation figure. Now, all of this we will do next meeting. So, by the way, before I miss, you have a different pressure drop correlation for random packing, and you have a different one for structured packing. And then we have here how to compute for the flooding velocity for this time, the tray tower. So you also have your specific procedure here to follow. So you obtain the tray factor. Okay, where is this tray factor? I'll show to you the illustration. This is the tray factor K sub B. You need the ratio of the liquid and the vapor flow rates, and you need the densities. As for the plate spacing, it is stated in the problem. Now, once you have already that one, sorry, that's the height already. So we're talking of diameter. So once you already have the tray factor, you determine the entrainment gas velocity. Now, this entrainment gas velocity it is said to be entrainment gas velocity. So meaning your gas carries with it liquid already. So it's already, your column is said to be flooded already. Because your gas should be pure gas as it leaves the column. But if it carries with it already liquid, it is said to be, there is said to be entrainment. And if there is said to be entrainment, your column is already flooded. So determining class the velocity for a tray tower, the flooding velocity using fair correlation is this one. You also see this in John Cookies. For organic liquids, we use 20 dyne per centimeter for the interfacial tension and 72 for water. So take note of these two values. Then you choose the diameter so that this gas velocity is just 70% of the maximum. So the computed maximum velocity here from this formula, you only multiply by 0.7 and determine the corresponding cross-section of the column using the volumetric flow rate. Okay? As for pressure drop, we have this one. So we determine the pressure drop when the column is dry plus this rho GH formula. Rho L, meaning it's the density of the liquid times the gravitational constant times the height, rho GL. Now we will discuss this in detail again next meeting before we go to the sample problems, because after this one, after the diameters, we'll go to determining the height of our columns. Okay? You have any questions?